This is the moment of truth for audio DIYers to use in the real world, the Loto instrument. That Loto instrument I have been talking so far in the past series 1, 2, 3, 4, 5, 6. This is a real bench test to use this Loto instrument, virtual instrument, in a Class A power amplifier real world bench test. This is a video with no pounds. Yes, guys, pounds, that's so-called LBS. Stay with this video and let's go for that. So everything is set up already here from left to right, and the only thing I can do right now is to power on the power supply with a plus 20 volt DC. Power it on, and let's monitor. The output signal is increasing and there you go. So I started at 26 degrees centigrade. That's a little bit hot on the heatsink, warm on the heatsink, I should say. Let me put that one into 0 volts and put that one into a 1 watt output power. The 1 watt output power is gonna be my criteria for evaluation. So what I have in here, I just need about 2.19 volt RMS at 1 kilohertz with an input signal that's about 272 millivolt RMS as an input signal and an output signal. So if I'm going to compute the one for the sake of understanding, 2.18 multiplied by 2.18 divided by the load of 4.18, so about 1.1 watt, that is RMS. If you want to say that way, I call it the average power. So this average power right now is where I'm going to have some analysis on the input signal versus the output signal. First thing is I'm going to see if my eyes is much better with the white background. It looks like it's hurting my eyes, so I still go for the black background and remove the grids. And there you go. Initiate the cursor, and the cursor suddenly pop off on my command. Alright, so I'm going to, let me put that way. This is the input signal, this is the input signal, the output signal, and at the peak of the input signal, we get the lowest peak of the output signal. And let's do that for 1 cycle. There you go. Yeah, it's 180 degrees out of phase from the input signal. That's what we can see in here. And I'm going to save that, just save it. And it's going to be like, it's a log input versus output, logs input, so that I can easily remember that. There you go. And I'm going to save also using the CSV. The CSV is in here. Save that, and okay, there you go. It's saved it. I'm going to what else I can do? That's already everything is in here. As I said, it's like magic. Everything is in here, and the only thing I can do then is to put that into square wave. So to do that, let's go to the menu, and I'm going to put the square wave signal into a square wave. So let me change that to square wave, and there you go, square wave, and turn it on, and you got the square wave signal. I set that to 2 let's say the output signal to be 2.1, which will give you an output of about 1 watt of power at 4 ohms speaker load, resistive load I should say. Sorry for the wrong words. And I can put that into full screen, and there you go. Again, it's still the same. The output lags the input signal with about 180 degrees. And everything is in here already. What else I can say except that this is 1 kilohertz, and there is one thing that I'd like to do is to measure the rise time of the output signal, and that's something that I can do live without the storage. What I can do is to capture, let's say, this signal in here. I want to expand that, and I can define the area, and there you go. That's not enough, so I still need to define the area, and probably that's not enough, and this one is too much, so I'm going back a little bit. There you go, and enable the cursor, and the cursor is pop in. We get at the starting point about 10%. At the rise of the square wave, I'm gonna take 10% of that, and then at the full rise time, I'm going to take, like, this is 100 and this is 90%. So 10% here and 90% there. So I'm measuring this this time. This is the rise time of the output signal. And what I can measure in here is that is the 0.002 millisecond. That will be like about 2 microsecond. Well, 2 microsecond. Just want to make it sure. 1, 2, 3. So 2 microsecond rise time signal based on my measurement. That's cool. So I'm going to save that one and say is a rise time output at 1, that is 1 watt. So I save that, and there you go. Save it. I also save it with a CSV. That's what I'm going to do also. And I'm going to find channel A, Loto, rise time at 1 kilohertz, 1 watt. There you go. I got the data, and so simple as that. Quiet, easy, ladies and gentlemen who is watching this video. Take a look at the temperature right now. So, oh my god, 78.6 degrees. It's really warm. It's really warm actually. 78.8 degrees at the top of the MOSFET transistor. So I'm going to save the one. I'm going to be like 1. Making sure that the original one, I'm not overriding it. And then the elapsed time, the timer is about 17 minutes. Let's put that side by side. At about 17 minutes, we got 79 degrees centigrade, from 22 to 79 degrees centigrade in 17 minutes. The other thing I can do is to rate the signal waveform in terms of the frequency from 20 hertz to 20 kilohertz. So I'm going back to the setting of the AF generator. I want to set the one to 20 kilohertz. That's 20 kilohertz. There you go. As you can see, it's compressed. At 20 kilohertz, this is the signal actually. I've got a little bit distorted at the input. I'm going to go for the rise time to take a look at this capture in here. Okay. Not so good, so I move a little bit and that's it. And then enable the cursor at 20 kilohertz. This is 10%, and that is at approximately 10%. So it did not change actually. It is in a 2.14 microsecond at 20 kilohertz. The rise time is 2.14 134 microsecond. If I'm going to do that in the, before that, I'm going to save it for my reference. This is at our rise time. And the next thing for me to do now is to go to 20 hertz. So I'm going to go again to the EXT, and I'm going to put that into 20 hertz. Let's go to 20 millisecond for the time span, and it is loading. Right, there you go. You can see that there is a heavy loss of attenuation on the low frequency. Let me fold that into a zoom mode. There you go, and I'm going to stop it. Clear up the cursor. So you can see, guys, this is supposedly a square wave, but we got a high attenuation of the low frequency in here, which is not a good thing if you wanted to maintain the bus in the lower frequency. So if you can see in here, this is the high frequency again for square wave signal analysis. The rising end is the high frequency, and the lower end of the square wave signal is the low frequency. High frequency, low frequency. Square wave signal analysis, something that need to take care on the hardware design to make it sure that at 20 hertz or the lower end of the frequency will be the desirable one, is as flat as practical. Okay, I'm going to save that one into something that I can remember it at 20 hertz. Let me just say something about the bandwidth of a power amplifier. We want a wide band so that it can cover from 20 hertz to 20 kilohertz, and that is really desirable for a full range amplifier, wherein a class A should perform a wide band from 20 to 20 kilohertz. And this amplifier, which is unknown to me, it's just labeled as a class A, the ACA from China market. It's an unknown, my first time to do it. My first time to test it, a demonstration for the OSC482, and this is what I've got. The thing that I'd like to stress in here is that the hardware should be improved to make the low frequency as flat as practical. The flatter, the better, because when I see that there is a loss on the low frequency, that means to say that for those purists or golden ears, they probably can hear that loss of frequencies in the low band of the audio spectrum, wherein for me, probably I won't be able to detect that or hear that. But again, in terms of electrical performance, the low frequency signal, the square wave should be as flat as practical. In this case, it's not so much desirable. That's it, I believe. That's it for the OSC4828's demonstration in a real bench test with a Class A power amplifier. I forget to save the temperature right now. I will see the temperature profile, which is quite easy with the DAQ. By the way, I'm using the UT71E from Unity. I really hope that the OSC482 in the future, they can put an add-on module that can able to measure the temperature, because in DIY power amplifier, especially in Class A, we need to understand about the temperature profile of a Class A power amplifier, Class AB, those kinds of things. Or maybe Class D, wherein it's less sensitive to temperatures. I mean is that less generating the heat on the heatsink. But Class A, this is notorious. I would say quite notorious to me, wherein the power is quite constant and the temperature is rise up rapidly that it needs a large heat sink in order for the power amplifier to survive over time. I cannot touch it. It's really hot. It's really hot. That is why I'm saying that how I wish that the OSC482 or any Loto oscilloscope can have a module that can interface into this oscilloscope, virtual oscilloscope that can able to read the temperature in degrees centigrade. And never mind the Fahrenheit, never mind for the Fahrenheit. We're not using Fahrenheit here. That's really what I can do right now for a simple demonstration in a real bench test of the OSC482 plus the ACA, the command version at Taobao. This is an e-commerce in China, and temperature logging, data logging, and also verifying on the oscilloscope in here, the original oscilloscope. I think this is finished. I'm going to turn it off now, the power supply, and there you go, it goes off. So I goes off also in this video.